Well, welcome all of you. Today, I have honor and privilege to introduce to you a true industrial leader. And when I say this, I really mean it. I have known Dr. Tony Dean for many years, and I have seen myself his influence within GE and outside GE. And presently, he is the Chief Operating Officer of General Electric, and he essentially has the portfolio which includes anything and everything in terms of R&D of a $150 billion company. So you are really privileged to hear from him. And the great part of that is he has a fundamental background in chemical kinetics. And I will tell a few things from his biography, which we would rather hear from him, because it will be a lot more fun when we hear from him. Well, he started with his bachelor's degree from McGill University in the field of shock waves. And the little background of that is, at that particular time, there was a 3 Mile Island incident that happened in USA. And that triggered a lot of research in the detonation safety. And that's where Tony started his work. And from shock waves to shock tubes, I'm very sure a lot of people over here are very familiar with Professor Ron Hansen from Stanford University. So Tony was part of his group, and he did some of the most fundamental and first measurements of prompt NOx as we know it today. Something with prompt NOx, because GE's Fenimore actually invented prompt NOx, or found out prompt NOx in the real systems. So, and later on, he joined General Electric in 1992, and due to some tube-body problem, which he may talk about, he had to leave, and then he came back to General Electric. He has led programs in many different areas: detonation, combustion, in CDN module for aviation, GE Aviation, which is essentially a compact module of combustor, diffuser, and nozzle. And later on, he became the technology leader for combustion systems in General Electric Global Research, post which he was the combustion discipline leader for General Electric Global Research, and finally, he is the CEO of this company. And I have a lot of fond memories in working with him and discussing with him. I have had many arguments with him also, and I tell you one thing, I always found out that he was right after 6 months or so when I did my own research. So he has amazing depth and breadth of knowledge, and we would like to learn from him a lot. And I think without further ado, please welcome Tony Dean.
Thank you, Sumitra.
My pleasure.
All right, is the mic working? Yes. Great. Well, thank you, and thank you for that very warm introduction. So I'm the COO for the corporate research, global research, in upstate New York. But it's really a privilege to be there and to be connected to the many products and industries that we touch. Just a couple are shown on this page. And really today I want to walk you through kind of the exciting times that we live in and just how much we've progressed over the last century and where we have to go. So this morning I want to give some context around power and propulsion. I want to talk about some global trends over the last couple of days. Some of them have been mentioned. Then really get into details of combustion systems and practical aspects of combustion, combustor design, and then we're going to have a workshop this afternoon where we actually go through this thought process around conceptual design. So let me just start with imagining the world that we live in. When was the first powered flight? Anybody remember? Was it 1800s? Beginning of 1900s. So 1903, the Wright brothers, and they actually hand-built a reciprocating engine. There were several things that had to happen to make powered flight possible, but one of them was a compact and relatively efficient engine to power that aircraft. And you think about that, that's a little over 100 years ago. Where have we gone? Well, jet engines first came on the scene in the late 30s, Frank Whittle and others in Europe. And in the US, that started in 1941. But pretty quickly, we learned how to make bigger and faster engines to enable supersonic flight and go Mach 1, 2, and then even 3. So just tremendous progress in the 60s. And then you say, what's the biggest engine we've ever had for propulsion? And that was an engine that's rated for 115,000 pounds of thrust. It demonstrated 125,000 pounds of thrust, but 2 engines power the 777, which was the picture on the first page. And if you think about what it took back in 1903 when we were just thinking about flight, if you were going from, say, Washington to Tokyo, that was 3 months, and now the world's much more connected, roughly 12 hours of flying. And for many of the people participating today, like myself, it was a flight that spanned 12 plus hours. And then if you say, where are we going next, it just gets better. There's a new engine called the 9X that replaces the GE90, which is higher pressure ratio, even more efficient, and that just had its first flight this past couple months as a test flight on a flying test bed. And those cycles and engines I'll talk about today, what's new and different. But it is just incredible to think in a short span of a little over 100 years, we're going from thinking about flying to today there's something like 300,000 people in the air at any given time, and there's a flight taking off almost once per second, commercial flight. So we really, this whole industry has formed in a short time, and it really enables the modern world that we live in. Think about power, same type of thing. We heard yesterday about the diesel engine, a little bit older than gas turbines, quite a lot older, and before powered flight. But if you think about gas turbines, which I'm going to focus on today, the first commercial gas turbine was at around the same time as flying. In fact, it happened earlier, 1939 in Switzerland, and that was a 4.4 pressure ratio. It produced 4 megawatts, and it had a huge thermal efficiency of 17%. And I'm being a little bit sarcastic with that 17%. But for the day, that was incredible. And relatively compact power compared to a steam turbine, which was the alternative. If you think about this year, so we're now well less than 100 years, and where are we? There's a great article that's cited in the reference here that talks about the 3 main manufacturers of large heavy-duty gas turbines, but they're all in the pressure ratio of 20 to 30. They could be higher, but actually they want to have exhaust gas temperature hot enough to drive a bottoming cycle. Their simple cycle power is hundreds of megawatts instead of just 4, where we started, and the combined cycle efficiency over 60% now. And if you do some quick math on Carnot and think about Carnot efficiency and consider what that takes, it's really astounding. And if you look at where the latest is, there was just an announcement of a Guinness World Record. Guinness has created a category with some rules around how you define efficiency of a power plant. And a combined plant, 3 gas turbines combined into 1 combined cycle plant, is 1,188 megawatts at an efficiency of 63%. This is in Japan. And just a quick question, if you have this much power, roughly how many households could you power with over a gigawatt of power? Anybody? More than 100,000? Yes? More than 1 million? Anybody going for more than 1 million? Yes. More than 2 million. The answer is about 2.7. If you look at the average consumption of a Japanese household, that 1 power plant is enough power to deliver power for 2.7 million people. Just incredible. And you think about that's one, probably fits on something like 10 acres of land, 10, 20 acres of land, and it can power more than 2 million households. So that's the world that we live in. And sometimes, you know, it's awesome to think about that. What is the science and technology behind those outcomes? So that's the world we live in. What's going on? First of all, competitive pressure. We live in a world of global companies that compete, and they really want to serve the interests of the world. And the way I think about technology is technology's role is to make a better world. You know, we want to have a better world tomorrow than we have today. If we're thinking about products, they want to deliver more than they did last year. We all know that with computers, and you know, phones went from phones to smartphones. We almost look at our phone not because it's a phone, but because of all the other functions that it does. And it's true in every industry. Every industry has a Moore's law of behavior. If you look at aviation travel, the cost per passenger mile continues to decrease. It's now less fuel burn per mile per passenger than a car. Now we go further distances, of course, but the efficiency is incredible between the airframe and the engines. So there's just incredible competitive pressure around making tomorrow a better day for all consumers. At the same time, we have to worry about greenhouse gases. We have to worry about clean air. And then we have, on the fuel side, just a whole set of changes coming as well. So I'll go into these in order here. First of all, you know, there is a lot of discussion about fuel usage. Discussion yesterday, is Europe going to ban, you know, the reciprocating engine for cars? And that may happen. But the other fact is shown here. This is from BP, their latest world report. You can look at any of the oil majors. They have similar reports. But if you look at every category of fuel, starting with oil, gas, coal, and so on, pretty much they're all going up. A slight dip in 2008 with the world economy, but they're all going up. Now, what's interesting and actually very exciting is the top orange, renewables, and renewables covers a whole span from hydro to solar to wind, and that's growing, and you'll see by 2035 that'll be a big piece. But what's interesting is pretty much every other category, if we stay on our current course, will also be growing. And so what that means really is the world is consuming more energy, and in every category it's going up. Coal's the one that we can debate, is it going to go down? And frankly, that might be a good thing as we look at the consequences of global warming and greenhouse gases. But why do we have that growth? And really it's because of growth in developing regions. And if you look at natural gas, we're finding gas is plentiful. We're finding new ways to extract it from the ground. And there's still 1.2 billion people on the planet without reliable power. So there's a need to help serve that need. Oil today, aircraft are powered by liquid fuels, and people like to travel, and it enables connecting the world better, and that is also anticipated to keep growing. So that's the backdrop. When you hear about what are we going to do in the future, the backdrop is it's really hard. There's a huge inertia, a huge installed base that will keep us on a track like this. And we need to do our part as technologists to minimize the impact of this. Global demand for energy means you get prices and price volatility. This is a chart looking historically. And what's really interesting is for years, once oil was sort of discovered, going back to really the turn of the last century, so late 1800s or 1900s, sort of in 2014 dollars is the light green line on top there. The cost of fuel was about $20 a barrel, and it moved around a bit, but didn't really go up until the 1970s. Took a huge spike, and that was sort of the first oil crisis. Then it came back and returned almost on a normalized basis to the same level, a little higher, jumped up again over the past 2 years, and then in the last two, it really dropped again. and now it's come up a little bit. It went down to about 30, up to about 60. It moves around, but the message here is that especially more recently, if you're an airline, if you're a power company, one of your biggest costs is fuel. Airlines, it's neck and neck between labor and fuel usage. The capital cost of the equipment is small. For airlines, it's probably about 10% of their total cost is the equipment. Fuel and labor are each between 30 and 40%. So for them, it's huge, and that's why the focus on efficiency, because every sort of gallon of fuel you don't need to buy is profit, and so they're interested in better technology. And that happens to go hand in hand with concerns about CO2. So here's, I was born in the early 60s, and you can see almost 100 ppm, 25% change in the planet's CO2 in the atmosphere. And there's a little bit of annual variation, but you can see the mean, the trend is clear, and that continues. And if you look at the sources of fuel, sources of the greenhouse gas above, you can see the lower part of that curve is green solid fuels, mainly mostly coal, liquid fuels, and then you'll see natural gas is there as the third largest. But natural gas has 4 hydrogens for every carbon, liquid fuels, 2 hydrogens for every carbon, and coal is pretty much carbon. And so you can see the contribution. If you're trying to reduce CO2, you really want to switch to fuels with more hydrogens. So methane is the best, and of course, one can imagine a day moving to hydrogen fuels to displace the others. So, as we look about how to make the world a better place, we've got to keep this in mind, and that's why the focus on efficiency is so key. In addition, we're becoming much more aware about global air quality, and there's a fascinating website. The link is on this page. And you can look in real time and say, what is the air quality around the world? And so this was just a couple days ago. And you can see in general, the US and Europe have pretty high air quality. And that's because of relentless focus on regulations. And, banning, in some cases, 2-cycle engines, going to cleaner burning 4-stroke engines. And then you can see in parts of the developing world, the emissions are higher. There are more than one factor. I've got some images here. These are NASA satellite photos. One of them the lower one is in the Middle East. That's a sandstorm. So you could argue that's naturally occurring issues that affect air quality. But above is off the coast of China, or China, and then moving into the coast. And there's really just dark, those darker images are really smog and smoke. And that's something that has a huge effect on people's quality of life. And you can see it with the numbers. If you take a look locally, I just went last night and pulled off a location. There wasn't data available in Saudi Arabia, but nearby. And actually, you can see this time of year, the data is pretty good. And you can see some of the metrics that are measured. So sulfur dioxide is a concern if you burn sulfur-bearing fuels. NO2 is part of NOx, and that can affect health in the form of asthma. Ozone also affects breathing and quality. And then PM10, that can be naturally occurring, just small particles in the air, but more often than not, that's man-made, that's soot, and often coming from reciprocating engines. So this time of year, good story, but I've looked at this at other times of year, and you can see high numbers. In fact, if you look in the upper corner, I've got the scale. They measure up to 500, and that's really considered hazardous, and they recommend people wearing masks. And you'll find places, if you look, that exceed 500. So there's clearly work to be done to improve air quality. And as combustion scientists and engineers, it's our job to from a technical point of view, to help fix the situation. So we talk about fuels. Mankind has typically burned what's available. And then we've learned that there's lots of things to find under the ground. What's new in the last 15 years is really the rise of unconventional natural gas. So it used to be natural gas would be found as part of a deposit for liquid fuel, and it might be a gas bubble on top of an oil field. But what we're finding is that gas is actually trapped in rock formations. And if you can drill down to those rock formations, typically shale, and if you can fracture the shale, you'll release high-pressure methane and connect it. And just to give you a sense of this is technology in action, typical shale will have a consistency and behavior a lot like sidewalk, cement sidewalk. And so when you hear about hydraulic fracturing, imagine what it takes to fracture a sidewalk and connect pores to enable gas to come out. That's what that industry is doing. And what you can see, this is just data from the US, but this could apply many places in the world. You can see that the proven reserves of natural gas have gone dramatically up, starting around the turn of the century, around year 2000. And the chart here on the right shows in blue, that's the contribution of shale gas to the reserves, and you can see it's just increasing. So this has been the first part of the world that's really exploited this technology and the knowledge that we can extract more natural gas. As you apply that other places in the world, where we're going to find ourselves truly is in the age of gas. That's going to be the fuel of choice. What you're seeing now is gas has been hard to move. You have to build a pipeline. What do? Well, it turns out if you are willing to pay about a 15% thermodynamic penalty, you can liquefy natural gas, and then you can ship it in refrigerated kind of form anywhere in the world. And it's had dramatic effect. It's actually for the better. LNG market now exists to move natural gas around the world. And for example, Asia, for years, the price of natural gas was over $10 per million BTUs, might be as high as $20. There's now long-term contracts for LNG at around $6 or $7 a million BTU. In the U.S., the price of gas is about $2 to $3 a million BTU. So that's just becoming economically the fuel of choice. As I mentioned before, environmentally, it's really a fuel of choice as well. So that's one sort of zone of change and interest. Another one is the growth of alternative fuels. A lot of interest in biofuels. And I think the interest kind of has been tempered by the reality that this is an expensive fuel. And it also, if you're not careful, can compete with food for people. So I think there's still a lot of questions about biofuels. There's great promise if you look at things like oil production from algae. 70% of the planet is covered with water. If you could somehow cultivate and grow algae in the ocean, that would be an almost limitless supply of fuel. So there's many ideas. Today, a lot of the liquid biofuels we have are things like ethanol, and that's good. It is a renewable source. In the U.S., about 10%, up to 10% of gasoline has ethanol in it. So you could argue that's renewable. But that's sort of a difficult way to create a biofuel. You have to grow corn. And then if you actually look at the thermodynamics of that process, a lot of the corn is fertilized. And where does the fertilizer come from? In fact, it comes from typically natural gas to create ammonia. So, some of the biofuels are not quite as bio as you might think. But they are replacements for fossil fuel. And in the future, I think they will continue to grow. So just to sort of recap, there's a bunch of trends, and what are the implications when you think about designing engines and equipment? First is, as I mentioned before, is there's really demand for a lower cost of total ownership. You don't expect to pay more for electricity tomorrow than you paid yesterday. You don't expect to pay more for an airline ticket next year than you did last year. So we really need to contribute to that, and we have by creating these advanced engines, which do lower the operating cost, and they have the added benefit of lowering CO2. Emissions regulation, I'll talk more about this, but there's been 25 years plus of really intense focus on emissions in many countries, just dramatic impacts, and that continues to be a constraint on the design. And then, more recently, the Paris Climate Agreement on CO2. We still don't know the full implications. What is the will of government organizations to make change? But they're certainly providing incentives toward fuel displacement and towards more efficiency. And so those incentives will carry through. So I'll just pause there. Any questions about this backdrop of kind of the world we live in and what the trends are? Yes, Bob. Here, I'm going to throw you the ball here.
You talked about that magnificent plant of how many gigawatts? 1 gigawatt?
1.1, yes.
Okay, Fukushima happened in what, 2012?
Roughly, yes.
When was construction on that plant commenced?
That's a great question. I can look it up afterwards. Probably in that time range. The thing about gas turbines is they are very quick, relatively quick, to be able to build and install compared to more conventional things like coal plants, which require a huge footprint and a lot of field assembly. Simple cycle can be put in 12 to 18 months. Typically combined cycle, you'd add another year or two. So probably right around the time of that was when they would have commissioned this plant.
Well, I'm suggesting that immediately following that. Okay.
It could be. It could be.
I think so.
And that's a good point. There are many countries in the world that have looked to displace nuclear power. I think it's an interesting sort of social dynamic of we're worried about CO2, we're also worried about nuclear. How do we balance that equation? Natural gas is a great intermediate spot, to be from my point of view. Other questions?
Hello. So when you're talking about the health implications of a particulate matter measurement, do you think PM10 is a good indicator of total soot in the air, or do you think like PM 2.5 would be better to use in terms of like how it would affect people's health?
That's a great question. The short answer is 2.5 is probably a better measurement. The smaller the particle, the more likely it just travels deep into your lungs. 10 microns, if you look at sort of Stokes flow, between drag forces and inertial forces, you really want to get down to the 2 and even lower micron sizes, and then it really does travel with the airflow. I think what's interesting about PM10 is the technology for measurement is fairly widespread, and so that map I showed earlier shows the locations around the world where those measurements are made, and the data is readily available. In fact, it's reported online, and anybody can take a look at it. I don't know much about the technology of measuring 2.5. I've personally been involved in laboratory measurements of emissions coming from engines, and I know they're not easy measurements. So I think it's really a question of measurement technology, what's reliable, what's cost-effective to enable widespread use. And I think that's a thing I could imagine in the future, that you'd pull up a website like this and find PM 2.5. It is more relevant to human health than PM10. I just don't know if it's more relevant or if someone's done a study of saying there's a good correlation.
Okay, thank you.
Yeah, thanks for the talk. You've presented the air quality here in the Gulf countries, but actually I was kind of surprised because the industries here are less than in the North America and also the power generation. Why the air quality here is less? Is this because of the sandstorms or because of the treatment of the air?
I don't know. In fact, there's not much data. On this public website, there was not data, for example, for Saudi Arabia, so I don't know the data. What I would say that you want to look at is what are your big industries and are they regulated in terms of emissions? For example, I think in this area, there are some cement factories, and the question would be, what are the emissions from, cement is a very energy-intensive process, and depending on where the energy comes from, that can create emissions, for example. I do think that the just natural landscape here, and that's why I had the picture of sandstorms, there are reasons to have poor air quality unrelated to what people do. So I just don't know. I haven't seen a study of this area. But I do think it's important to look at what the standards are, and are we following standards as we go around the world. As I'll talk earlier for gas turbines, unregulated gas turbines, going back to, say, the 1980s, typically would put out 200 part per million of NOx. We now have technology, and I think Professor Dubel mentioned this in his kickoff, we're down to 2 or 3. I'll mention later, 3 ppm is what you can achieve in the combustor. In the US, that's not good enough. They mandate 2, which is typically requires selective catalytic reduction, SCRs on the back end. So you really have to look, when you ask the question, is local air quality affected by people? I'd ask the question, when you have plants, what do they put out? And it can be orders of magnitude higher, and that can be contributing to the brown haze. When I was little, I remember visiting Los Angeles, and Los Angeles is in a valley with a lot of sun, and you would just see this brown layer, and it got to be more and more days per year had that brown layer. Since that time, I think nowadays that still happens on the occasion, but as far as I know, it's something like less than 30 days a year. They've really done a tremendous amount to clean it up.
Well, this is a long pass for me, okay?
It might require 2 hops,
I have a question regarding the gas turbines. Are we reaching the saturation point? A 60% efficiency is very close to the second law of thermodynamic limited efficiency. Maybe is it time to look for another breakthrough in aviation power propulsion or something like that? What do you think? I'm looking for your comment about it.
I'm constantly amazed by the ability of humans to innovate. I guess I would just say that. When I started, we talked about 60% for many years. So I started at GE in the early 90s, and there were discussions. There was a program called, the Advanced Turbine System. The U.S. government, Department of Energy, sponsored a lot of research. And our quest was 60, and we thought, wow, that's going to be hard to do. And it was hard to do. And we actually, technology evolves in ways you don't anticipate. So one of the ideas was to use steam cooling instead of air cooling, and that would be the way to get to 60%. And it was mostly true. We got very close to 60, and depending on the day you measured, maybe it made 60. But the fact was that steam cooling was complicated, expensive, lots of piping. It wasn't, in the end, the preferred way to get to 60. What's interesting in the last 5 years is all 3 major manufacturers of large gas turbines have found ways to really get comfortably above 60, not just have it as a milestone. I mentioned this record of 63, which was very recent. When you look at just basic thermodynamics, you mentioned we're reaching entitlement. I don't think that's true. I think we have a ways to go. We have right now 2 cycles, the Brayton cycle sitting on top of the Rankine cycle. Imagine a topping cycle. Imagine something on top of the gas turbine where the output of that topping cycle went to the gas turbine, then goes to the Rankine cycle. So in my own mind, I can see a path to 70. Not easy, but just for all of you starting your career, I think you should set your sights on what would it take and how would we get there. I think the more interesting question is, do we want to be burning fuel? I think that's going to be the big choice that we make. And with the rise of renewables, and I'll talk about that, I think that's going to be a basic choice. But I think renewables will not, at least in the current form, enable the modern world that we have. So I think there'll be a balance between both modes. And so it could be that power production from burning fuel goes down as a percentage. In the total planet, it'll be debate whether the magnitude increases or decreases. And I do think that there's a path to higher than 63%. And it's incumbent upon companies to try to do that, but also a lot of help from universities, from national labs, national governments. These are hard things to do. These are hard machines to make. And it's really a team sport to have the right suite of technologies to get there. One more in the back, I think.
Hi. So you've shown one plant there that's 1.1 gigawatt, that's very large. Yet there seems to be a lot of talk of the trend of decentralization, micro turbine CHPs. Their efficiencies aren't so high. But obviously that kind of localizes the requirement to meet the emissions, and the customers are local. It allows a certain amount of fuel flexibility. Do you think those kind of micro plants are going to reach the high efficiencies as well, or will there always be a price to pay in efficiency, but obviously you have it local, so it's meeting this decentralization idea?
That's an awesome question, and I think it leads to the thought that energy really is decentralizing. You know, just like, you know, when I grew up, if you wanted a telephone, it involved having a landline. And so, and in some countries that was easier and harder than others. But landlines were very effective, but they also cost a lot. The cost of a telephone as part of your salary was bigger 40 years ago. And I think it's interesting to look at how cell phones have displaced that. You know, countries in Africa don't maybe have the same cell phone infrastructure, or sorry, landline infrastructure that US or Europe has had, and they don't need it because cell phones deliver everything that landlines used to deliver. I think energy is going the same way. So when you have areas with millions of people, if you count the number of cities that have more than 10 million people, and there's a growing number of those cities, they just need a lot of power. And cities run 7/24. You know, they're just all day, every day. There's a lot of infrastructure that just needs to keep going. I think in those places, you're going to have centralized power. You need, now it could be local-ish to that city, but you're going to need big centralized power like I just talked about. As you get further from those population centers, it's an awesome question, and I think where the infrastructure does not exist, it'll drive towards smaller power units, a lot of more maybe renewables and renewables with batteries. You asked a question, the efficiency of small engines. For me, it's a thermodynamic problem of surface to volume ratio. If you look at engines, you know, the smaller they are, the more important the surface area is, and if you have hot gases, those hot gases lose heat to those walls. So at some level, there's almost a basic surface to volume trade. But within that, I think I've seen some very innovative engines and engine cycles that minimize that heat loss. And I think we're going to see a day where the efficiency of small engines rises to 50% plus. We heard some yesterday as it relates to transportation systems and recips. When you're above 50%, and then you imagine putting that right at the point of use, that gets interesting, because today transmission and distribution loses 10, 15% of the megawatts that go in, you know, don't make it to the end user. So the effective efficiency is lower. You can be 63% at the plant, but what are you when it reaches its destination? So if you have smaller power production, then that 50% but no T&D losses, that starts to get very, very competitive. So I think we are moving to a world where it's going to be diversified. And what's interesting, though, when you ask the question, when you have a gigawatt plant, how many people work in that plant? And it's typically a handful. It's just incredible productivity. If you have small power, you know, what's the reliability of the small power plant user? And as a percentage of the power they make, they're more demanding. So I think there's a real trade around total cost, but there's nothing like resilience and energy independence. And so that's what's going to drive, I think, also smaller power. So I think the answer is both. It's just a debate in the future will be what fraction.
Great, thank you.
Laptops should be closed anyway, shouldn't they? All right.
Okay, thanks for your talk. Yes, I just saw the emissions of PM. My research focused on the diesel engine for low temperature combustion. So my question is that, the emissions of the PM is the same, the formation mechanism is same to the diesel engine or not? And then I saw the NOx and the PM together, right? Is there any trade-off between NOx and PM in the gas turbine? I mean, if the combustion temperature is high enough, that can be form the NOx, and then I think the PM can be burned out, something like that. I don't know.
Yeah, no, the fundamentals of particulates are very different between a gas turbine and a reciprocating engine. So the way I think about a typical diesel, you squirt fuel in, it's pure fuel, it's going to a very hot environment, and initially there's not enough mixing of the fuel with the air, so you make a lot of particulates. And then during the course of the actual power stroke and the subsequent combustion, you remove a lot of the particulates by oxidation. So particulates actually come out of the engine are the difference between two big numbers, a big formation rate and a big removal rate. And it's that relatively small delta of what we actually see coming out. In a gas turbine, there's different combustion systems. I'll talk about them. In historic gas turbines, we have diffusion combustors, which have a rich zone, and then typically dilution air, and then you mix a lot of air, and kind of like a diesel engine, you make particulates, and then they get oxidized. And that's true of many aircraft engines. But in modern gas turbine engines, we premix the fuel before any combustion happens. And so the initial formation is just dramatically lower. So typically a gas turbine has much, much lower particulate levels, even if it has a diffusion combustor. They have, just relatively speaking, a much longer residence time to burn that out. So it's true that for gas turbines in my career, most of the focus has been on NOx. We haven't really had to worry about particulates. It's just very low levels. And that's a place that reciprocating engines need to go and can go. If you look at some of the technologies that were discussed yesterday, orders of magnitude reductions in particulates, right? That's the promise. And I think that's the clear direction that we need to move that technology to. Great, I'll have time for more questions later. Let's talk now about sort of what the implications are from a technical point of view. This is a combustion short course, not a thermodynamic short course. But I do want to just take a moment to talk about the Brayton cycle, because it's just so fundamental to gas turbines. And I'll focus on this TS diagram, temperature versus entropy. And this is just very important to sort of everybody be grounded. The cycle points 1, 2, 3, and 4. If you're in this industry, you'll hear a lot about T3 and P3. These are the temperatures and pressures that are the exit of the compressor. Actually, this isn't exactly the same terminology. Often 2 is the exit of the compressor would be 3. We add heat up this line to some peak temperature, and then we drop it down through a turbine. So the combustion process is here. It's following a line basically of constant pressure. This is an idealized view of the cycle. There's a couple of key losses that become very important to talk about. One is if you have an imperfect compressor, you're going to end up coming more at a diagonal, and you'll end up at a higher compressor exit temperature than you would if you had a very efficient compressor. Likewise, after the combustion is over, if you have an inefficient turbine, you'll end up not extracting all the heat, and so you'll end up with a hotter exhaust than you planned. And then if you're not careful, if you have a combustor that has a high pressure drop as the air goes through that system, you'll actually not be constant pressure, and you'll fall off. So for a gas turbine, component efficiency is very, very important. In fact, that was the thing in the 1930s that really made the difference between a Brayton cycle as an idea and a Brayton cycle as a practical technology. It was really learning how to compress air efficiently, and then having turbine machinery in the back end to expand it efficiently. And the combustion, of course, what's important is you have to burn all the fuel and get that out as heat. The other thing to note when we talk about efficiency, in a combined cycle, what we're really saying is we take the energy that comes out after the expansion and we put that into a bottoming cycle, typically a steam Rankine cycle. There can be different pressure levels. Modern and efficient systems are up to 3 pressure levels to extract as much work as possible, extract as much energy out of the exhaust stream. There are other ideas for ways to extract that energy. There's a Rankine cycle, but based on different working fluids. A lot of work going on now with CO2. CO2 is interesting as a working fluid because it has high heat capacity like water, but in many parts of the world, we're in one right here where water consumption in a plant is costly and expensive. If I can have a closed loop with, say, CO2 as a working fluid, that could be better. And so there's some interesting work going on different bottoming cycles. But today I'm going to focus on really the process to go from the exit of the compressor to the inlet of the turbine. That's the focus. And it is dictated, though, by the choice of cycles. As we go to higher pressure ratio cycles, we need to have combustion happen at those pressures. What's interesting is if you look at rockets, in my childhood, the Saturn V rocket was the technology that got man to the moon. And if you look at the pressure ratio in that engine, it was high, very high compared to what we think of the other technology at that time. And the Saturn V rocket had a mission. It had to burn for 180 seconds, about 3 minutes, without blowing up. It had to work once. If you look at modern engines, I mentioned that 9X engine that's under development, its pressure is beginning to approach the pressures of a Saturn V rocket, but that's intended to work for thousands of hours, for thousands of flights, for thousands of cycles. And so we've moved to a place where we're now at pressures that are very high, and in fact, the basic data, sort of the combustion data, when you think about Briggs and what our foundations are of our technology, we're now moving to a place where we don't have very good elementary rate coefficient data. We don't have very good images of what does a flame look like when you're at 50 bar, 60 bar higher for a gas turbine. And that's the opportunity, I think, for universities, for national labs, to really help us to get the basic knowledge. What changes? I'll give you one thing to think about. We use liquid fuels, and we think, well, liquid fuel means it has surface tension. It means that you have to atomize it. You have to evaporate it. Well, what happens when you go to a pressure where it's no longer a liquid? What happens when it's actually more of a supercritical fluid? How does mixing change when you have supercritical properties? That happens today in reciprocating engines. The liquid fuel starts as a liquid. It's relatively cold, but it's entering a temperature and pressure environment where very quickly it's transitioning. And for recips, we're sort of used to it. For gas turbines, key question. How does the basic mixing and combustion phenomenon change as you move from a liquid that we kind of know and love to supercritical properties of fluid, which we don't really understand, is it different or not? So that's why thermodynamic cycles are just so important. It can move you from a zone of comfort where you have a lot of knowledge to a zone of maybe discomfort where there's more risk and more unknowns. And so that's really what's driven a lot of sort of combustion development, is really understanding as we evolve cycles, hotter, higher pressures, what does that mean? So, I just really talked about this chart. What are the drivers of high efficiency? It is about higher temperatures. It is about higher pressure ratios. It is about component efficiencies. And this is a theoretical chart. If I had just ideal cycle, ideal working fluid, this would tell me that as I go to a pressure ratio of about 25, that in theory I could get 60% thermal efficiency. What's amazing is with all those losses I told you about, we're getting towards numbers like 50, and it takes having a bottoming cycle to get you now to 60 and above. But to the question earlier, what this curve shows you is it is flattening. And so for the sort of same effort, you're not going to get as much. Or the other way is to say to make a big change, it's really a lot of effort. And that's the challenge in front of us. The good news is we have better tools. If I think about when, 1940s, that first gas turbine at 4.4 megawatts in Switzerland, that was probably designed with a lot of hand calculations and slide rules. And today it's like, what's a slide rule? So, we've come a long way from slide rules to help us with calculations to computers, and we need all of that help as we go to higher and higher cycles. So here's sort of a great chart just to show how the world has changed since the 1970s when industrial gas turbines really came on the scene and became a big part of power production and for mechanical drive applications, so-called EClass. And here you can see EClass was characterized with a firing temperature of somewhere around 2,000 Fahrenheit. And what that really meant is that you could have hot gas from the combustion go into a turbine, and that turbine could be uncooled. So it's uncooled technology. There are metals, nickel-based alloys, that can withstand that type of temperature for thousands of hours, and you can make power. So that was sort of the big technology of the day, was finding the right metallurgy and alloys to enable E-class technology. And you can see, put into combined cycle mode, you're getting 45, almost 50% efficient. And in its day, that was very competitive. Coal plant might be 30% efficient for the pressure levels and temperatures they ran. And then starting in the 80s, F-class technology, that's really the introduction of air cooling in the turbine. So now you have airfoils with holes in them and your pressurized air bleeding through, and also the advent of sort of thermal barrier coatings, putting a coating on top of the metal so that now you get to a point, if you're 2400, you're now operating above the melting point of the metal that's actually extracting the work. So that's sort of an interesting thought. Very high velocity hot air is what's coming out of the combustor, and you're able to extract work even though the materials themselves cannot take that temperature. It's because of the air cooling, because of the thermal protection. H-class, I talked about the steam-cooled H. That was in the early 2000s, and that got very close to 60%. Again, another step in temperature. That reverted to steam cooling of the hot gas path parts. So instead of holes, it was just backside cooling. A very elegant solution, and it worked. But if you think about ducting another fluid, you think about how to put it into rotating turbine machinery. If you think about all the piping required to get steam at the right conditions to the right place at the right time, and then do it reliably, it was just expensive. So the industry kind of stalled out for a while, but the dot that I just put up there in the corner is what I talked about. So the HA, and there's two worlds when it comes to power. There's a 50 hertz world, there's a 60 hertz world. And so last year in 50 hertz world, a record of 62.2, and then this year on the 60 hertz world, 63%. So that's just remarkable. And the firing temperatures are higher. And what it really means is, we have very good, counterparts in technologies around materials, around thermal protection, around air cooling, so that we can now have parts that are probably the air flowing around them is something like 400 degrees above their melting point. If you were to stop that cooling flow, you'd melt that metal. I heard a calculation from one person, about 15 seconds. So the parts won't survive if you're not cooling them actively all the time. So that's just an amazing sort of progression. And as for the question earlier, what's next, right? And that's really for all of you to start to contemplate. What do we do in the future? So I want to move now to sort of combustion and emissions. And this is a great chart put together by a colleague of mine to really help think through, if you start with fuel and air, hydrocarbon fuels, if you make the small a there 0, it can just be hydrogen. But you really have your reactants. In any engine, air-breathing engine, you're going to have fuel and air, and those are the main constituents coming in. In the middle, you have normal products of combustion. So CO2, water, nitrogen, and most engines, many engines run with excess air, so they'll have some oxygen coming out the back end. And then when we talk about emissions, really what we're talking about is these unintended consequences of combustion. Unburned hydrocarbons, soot or particulate matter, CO, and then the oxides of nitrogen. And if you sort of separate that, some of those unwanted products of combustion are from the fuel, and some are just from the air. And it really helps to distill it down to these fundamentals, because once you understand the fundamentals, you know where to start. So for example, if the problem is particulate matter, that's from the fuel. So probably it has to do with mixing of the fuel. And we talked about for diesel engines, it's hard when I inject pure fuel into really hot air. It's really hard to get the mixing scales fast enough before chemistry starts. You know, if you're worried about oxides of nitrogen, it's just fundamental to heating up air. And you know, the reality is we have an atmosphere which is 80% nitrogen, 20% oxygen. You're not really going to change that equation. So you have to say, well, how do I deal with that? And as we talk about in the future, sort of some of the, in the next upcoming charts, if you think about what we do, it really helps to just have this very fundamental view of where do these different emissions come from. And breaking the problem down like this can really help point you to where to put effort. So if you take a look at sort of what comes out of a gas turbine, and this is a nice table that really starts to talk about that. Start at the top, the major species, oxygen, nitrogen, carbon dioxide, and water vapor. And those are the typical volume levels. I would say that with oxygen coming out the back end, different countries have different ways of talking about emissions and the emission standards. In the United States, they've normalized the amount of emissions to 15% oxygen. Because if someone said, well, I'm limiting you to 10 ppm NOx, if you have enough air and you just dilute, you could get any number down to 10 if you just dilute. So, but if you normalize back and you correct back to a standard, now you hold everybody accountable to the right number. But today's engines, that standard came in when we had lower firing temperature machines. As we go to higher firing temperatures, you know, the amount of actual oxygen coming out the back end is lower than 15%. And there's some cycles I'll talk about which involve reheat. You actually have, you know, an expansion on the Brayton cycle is a reheat cycle where you burn a second time inside the gas turbine. And in principle, you could burn all of the oxygen from the engine. And that actually might be a more efficient from the point of view of if you did all this work to compress the air, especially if it's not perfectly compressed, I might get more total efficiency if I have combustion that leads to removing all the oxygen. In terms of the minor species, we talked about nitrogen. What's interesting is in the 70s, there were some real issues on gas turbines because the fuel supply wasn't clean. You had sulfur in the fuel. You had fuel-bound nitrogen. You had other contaminants in the fuel. And what the world learned was that for these sort of finicky gas turbines, you have to treat the fuel, and there's a pretty rigorous fuel specification. Reciprocating engines typically are much more forgiving in terms of the type of fuel they can burn and the level of fuel contaminants. So sulfur dioxide, often, especially in many engines, any engine that has complete combustion, you're going to get as much sulfur dioxide out as you had sulfur in the fuel. And if you look at some of the heavy fuels, they can be 2% by mass sulfur. So sulfur's not a nice product of combustion because it can lead to acid rain and smog. So dealing with the fuel even before it gets to the engine is an important thing to do. And also, just not on this page, but you do have to worry about other elements in the fuel. One that plagued the industry in the 70s and 80s was vanadium. Vanadium forms vanadium oxides that are extremely corrosive to metals. And so if you have more than trace amounts of vanadium in an engine, you have to worry about that. In fact, there's some research going on at KAUST to look at, can we understand better the implications of vanadium and what the real limits are? Because in the 70s, we learned it was not a good thing and had a knee-jerk reaction to just say, well, let's not have any. Now we're asking the question, well, how much could be acceptable? Those are the kind of research questions that we have. And the whole science of what are fuels and how are they compatible with engines is a very, very important area. If we look at emissions requirements, standards vary tremendously all around the world. And even in the US, you'll have national regulations, and then you'll have local regulations. And then you have even variations on that. You have so-called ozone attainment regions and non-attainment regions. And so if you're in an ozone non-attainment region and you want to source a stationary power plant, different rules compared to where there is no ozone problem. And ozone is one of the things that goes with NOx emissions to create conditions that are bad for humans, for breathing. So to help you just think through what are the standards, World Bank is one vehicle for global standards. Many power plants are financed by the World Bank, and so their rules are: we'll lend you money as long as the equipment you put in meets the requirements. And what you'll see in the categories on top is particulate matter, NOx, sulfur dioxide. And if you look at the applications, engines, reciprocating engines, gas turbines, and boilers. And you can also see the standard as it relates to the excess oxygen. And it's just interesting, boilers have been given, you could argue, more of a pass than gas turbines. Gas turbines are the lowest. And 25 ppm for natural gas is sort of standard. I'll show you examples where we've really made progress, and we can go well below that. Now, as you go to hotter firing temperatures, there's tension. It's hard to achieve those without after-treatment, but that's the fun of combustion science. So this is a great sort of reference to look at to say, what is the global standard and how does that apply? In a similar way, aviation has emissions requirements, and there's a United Nations body, ICAO, that sets the standards. And you can see over the years, we're now falling under so-called CAPE 8. And this is actually a very interesting chart to look at because it isn't just one number. There's actually some complicated sort of algebra to get to these numbers. First of all, the NOx standard is based on a landing and takeoff cycle. Most of the motivation here is air quality around airports. So NOx emissions at altitude, at cruise, is today unregulated. And in fact, there's a debate. Is NOx at high altitude a bad thing or not? According to these standards, they just are not looking at it. So they're just looking at what are the standards around airports. And you can see if you take the gray triangles, are data from what's in production, and look at the blue, those are more recent certification data across all the companies. And you can see that the new engines have a lot of work has been done by combustion engineers to lower the emissions while having tremendous increase in efficiency of those engines. So this has really been a victory. The other interesting thing about the standard is you see the bottom axis is overall pressure ratio. And so it actually allows for more emissions for higher pressure ratio engines. And that's sort of an acknowledgement that higher pressure ratios typically also involve hotter engines, and it gives it a little bit of a pass when it comes to emissions. So this is really the only standard I'm aware of that has a sort of an efficiency correction to the NOx standard, because in the end, both are important. The final thing I'll say about this standard is if you look at ground-based and you say, well, what's our best liquid-fueled combustion system on the ground? And you are down around numbers like 10 on this scale. So we have the technology to get low emissions for aircraft, but obviously aircraft are mobile, and we're very concerned about safety. So getting an efficient and very reliable and very safe technology, that's the opportunity. The opportunity is to take what we know ground-based and move it into flying engines. There is talk of another CAPE standard, CAPE 10, and the type of change will probably be between 20 and 30%. So we can imagine for 2025, this will come down yet again. But right now, the standards, a lot of discussion in the standard setting community, is the focus NOx or is the focus CO2 or is it particulates? And in the end, the rules get made around all three of those. And so thinking about CO2, and CO2 is an emission. It's a naturally occurring, you could argue, when you burn hydrocarbon fuel. But here's really where the aviation world is focused. And this is, again, there's a nice reference here. But the industry took a look at the Paris Accord and internationally and said, what does aviation do? Because as aviation is a contributor to greenhouse gases, how do you make that better? So this is a great chart just to look at what are the scenarios going forward. And so I'll just guide you through this thinking. Total emissions of CO2, if you sort of say, where are we? We're on this trajectory of about 3 to 4% growth in global air traffic per year. And if you just project that out, you still have the no action line, and you'll say, wow, we're going to, the aviation industry will start to become a bigger contributor to CO2. Today, all of air travel is something like 3.5% of the world's CO2. So it's relatively minor. But as the world displaces carbon, from other, as we decarbonize energy, perhaps start to decarbonize, ground-based transportation, the contribution from aviation will be higher. And so the blue area is really about making just operations more efficient. And so this is about using GPS and having flights be more direct. I remember a day when you'd be in an airplane, a big airport like, say, Chicago, you'd get close to it, and then you'd be on a spiral. And you might take 30, 40 minutes up in the air waiting to get your landing slots so you could land. That happens very seldom now. Much more focus on connecting directly. So a lot of technology around sort of movement of aircraft, taking into account weather, and adjusting to minimize fuel burn. So that blue is, if that's done across the industry, that's what could happen. The orange here is aircraft technology, which includes engine technology. When you hear about a new model of aircraft coming out, the most recent, you had Boeing with their 737 moving to their 737 MAX, Airbus similar with the A320 to the A320neo. Neo was new engine option. And in both cases, the airframers pretty much left their airframes as they were. They made some tweaks, but most of the improvement in efficiency was the new engines. And those engines delivered about 15% lower fuel burn than the engines they replaced. And that's typically the standard in the aviation business. You got to be somewhere between 15 and 20% fuel burn reduction to make it worth the literal billions of dollars it takes to design, to make reliable, and then to certify those aircraft platforms. So what's exciting from my point of view is we've just gone through that new engine option cycle. The leading manufacturers of aircraft and engines have been successful doing that, and we see path to another 20% reduction. And so again, going back to the question is there room to do better? There is room to do better. I think next time it'll be a little bit more on the shoulders of the aircraft manufacturers. How do you think about more efficient wings? How do you lighten up the whole aircraft? So it's a team sport between the engine suppliers and the airframers, but there's clear path with aircraft technology to get on the orange curve. But you can see at the bottom here, there's really a market for thinking about different fuels. And if we don't do that, we're going to go from this goal of being carbon neutral growth after 2020 to having aviation be sort of a bad guy. So this is another area of opportunity and another area of real growth. If, as a technologist, and you say, how do we help? This is a great place to be focused and to be helping. So just to summarize this sort of section, you think about the mix of fuel types in the future. I think I just want to spend a moment talking more about renewables. Because, when I grew up, people thought, oh, wind turbines and solar, but very expensive and probably not that reliable. What's interesting today is that both those are changing. There are now wind turbines that are just massive in size. The largest onshore wind turbine that's been announced is 4.8 megawatts, and the largest offshore wind turbine that's been announced is about 12 megawatts. So still small compared to those gas turbines I told you about, but that's one turbine standing up in the air, either on ground or offshore. And at those scales, the cost of electricity normalized is competitive now with, say, a gas turbine with fuel. So it's getting to be a very interesting dynamic between, if I want to, replace, say, a coal plant that might be old, and actually coal is becoming more expensive than natural gas in many parts of the world. Do I convert to gas, or do I go straight to renewables? Because once I buy that wind turbine, that solar field, I don't have to. I've got sort of 20 years of power without paying a fuel bill. The thing that's still a difference is that renewables are not so-called dispatchable. If you want to have power when you want it, you want lights on today, right now, because we're here, can renewables do that? I think what we're going to see is the rise of energy storage. And so the combination of energy storage and renewables will start to be a bigger and bigger part of the grid. But the other factor to think about is a lot of the equipment that we have lasts for 30, 40 years. So even if this is cost effective, the penetration into the market will be relatively slow. So it takes a long time to change. But what that means is there is market uncertainty for new engines. And so companies are really grappling with, do we go renewable, or do we make new engine technology? I think the answer is both. And it's really incumbent upon engine makers to demonstrate the value, both from efficiency and from an emissions point of view. And really it creates an opportunity for biofuels. What's interesting about methane is methane can be extracted from the ground. I talked about shale gas. But methane can also become a byproduct of agriculture. We can create biomethane. And so you can imagine a whole economy which starts to not use fossil fuel, but still has renewable fuels. And whether it's bio-enabled or whether it's some other process, hydrogen is another fuel that's talked about. I think the challenge for hydrogen is how to make it cost effectively. But between hydrogen and biofuels, that's really the huge opportunity to displace, at the end, fossil fuels. And then the age of gas I talked about, that's just the other reality that it's winning economically in many parts of the world, and that'll continue as gas reserves are exploited. So that's sort of the thought about now getting into the technical drivers. I've got let me just finish the thought here on biofuels. I mentioned ICAO as a standard setter for emissions. They're worried about not just NOx, but CO2. But here's a timeline of what they've been doing. And really, they've got a program to look at fuels, and there's routes to do approvals of fuel. And so now, fast forward to where we are, 2018, we have a number of fuels that are considered sort of drop-in replacement for jet fuel. And some of them are bio-derived, and some of them are, say, Fischer-Tropsch fuels. Fischer-Tropsch is where I can take a gasification process and sort of create a liquid fuel from the ground up, from hydrogen and CO. I can use catalysts to make a liquid fuel. So really, the aviation industry has been a champion and a supporter of developing standards and alternative sources of supply, so that an increasing amount of the world's aviation fuel can be derived from sources other than fossil fuel. So that's exciting. And to bring the sort of the question then is, well, how does that affect combustion? can you really have a drop in fuel? So this is a chart that's been used by the National Jet Fuels Combustion Program. This is a consortium in the US. And if you look at the properties of fuel, things like the density of the fuel, the viscosity, the surface tension, the vapor pressure, the heat of combustion, but then other things are important, like the freezing point. If I want to use a fuel, the question is, if I fill my fuel tank and then it stays in a hot or a cold place, what happens? In a hot place, I worry about vapor pressure. In a cold place, I worry about, will it still be a liquid? So the blue boxes are really all of the things that matter that are intrinsic properties of the fuel. Then the things that happen inside the engine, right, I atomize, I evaporate, this chemistry. And the question is, do those happen in the same way? And what's interesting is Jet A is simply a specification. It's a specification of properties such as the ones listed here. It is not a pure chemical substance. So when you want to replace sort of a distillate-based fuel with something that's not distillate-based, you end up with, well, how does this connect to what happens in the engine? And I'll talk more about this later in terms of the requirements of a combustion system. But in the in the green, these are some of the things that we worry about. Can I start the engine? Will it light off? What will the emissions be in terms of particulates and emissions? Where will the flames sit? Will it be closer to my metal walls? Do I have to worry about the temperature of the liners? How does the flame structure change the temperature profile coming at the back end? Today, there's a very tight integration between what comes out of a combustor and what goes into a turbine in terms of a temperature profile. If that changes with the fuel, I could suddenly find that one fuel led to different life. I worry about combustion instabilities, and then there can be properties like coking. The good news about many of these bio-derived fuels or Fischer-Tropsch fuels actually is they tend to have less of the impurities. So I'd say over the last 5 years, we've learned that many of these replacement fuels actually look pretty good, and there's not nasty surprises. But as technologists, we've really got to go through this detailed list and make sure that that's true, because you don't want to find out, in the application. So the takeaway here is that there's many linkages between fuel properties and the combustion performance, and that's an important part of how we need to do our work as we think about the future. So one more discussion around fuels, and that's alternative gaseous fuels. I was visiting Saudi Arabia a couple years ago and had a great discussion talking about fuels. And really, there are a number of fuels available in the kingdom. There is natural gas. There are various grades of crude oils and then refined products. But there's also other fuels. And so this is a great chart to help you understand how you characterize gaseous fuels. So just like liquid fuel have properties we worry about, one of the key parameters, or two key parameters for gaseous fuels are shown here. One is simply the heating value. So per unit of mass, and I apologize for the maybe the English units, but industry happens to work very much still in English units. So heating value expressed in BTUs per pound, and then a thing called modified Wabi index. And the question is, what is that? And that really relates to, I got the equation on the side here, that's your heating value, but normalized by the molecular weight of the fuel. And then it's actually modified Wabi. So Wabi index pure is just that. It's a normalized heating value by mass or by specific gravity. But it's also modified in this case to include temperature. And the reason that's important is modified Wabi index really relates to the volumetric flow of gas that I have to put into an engine to run it. And the reason that's important is when I'm designing a combustion system, I have to design air passages for the air, fuel passages for the fuel, and a key parameter is what is the velocity of the fuel in the fuel passages. If the Wabi number changes, say by a factor of 2, that means the velocity of the gas going through it will change by a factor of 2. And because pressure drop goes as velocity squared, I can suddenly find myself, if the fuel is less, it has a lower heating value, a lower Wabi number, I can suddenly find that velocities in my fuel system don't make sense. I can't push enough air in because I suddenly get surprised by the pressure drop. And then that can also relate to the combustion operability and performance. So this is just a, if you reference yourself on natural gas in the middle of this chart, and then you say, well, what's different as I change fuels? One is to have a fuel that just packs in more energy by mass. That would be hydrogen. And that's often a consequence of things like refineries. So sometimes there's diluents, but also you can also get pretty high levels of hydrogen. And hydrogen is a very reactive fuel. So if I'm trying to do low emissions, I suddenly have to worry about the reactivity of that fuel in terms of, is it going to cause flashback? Is it going to have flames in different places than I was expecting? So that's one axis of when I have a different fuel. If I have heavier element C2+, so that's like 2 carbons instead of 1, I just get more heating value. It's sort of becoming a liquid. The vapor pressure is lower than methane. This is becoming very interesting in the United States. With the rise of unconventional natural gas, we're getting more and more condensables coming with that gas. So it's not just methane that we're extracting. We're getting methane plus ethane, ethylene, other compounds. So those C2+ are very good fuels, propane. But if I'm expecting natural gas and I get these heavier stuff, I have to worry about will those gases condense somewhere. If I have a control valve leading into a plant, typically that control valve controls the flow and there's a pressure drop. And if you actually look at the temperature history through a valve, often there'll be a temperature depression. You might lose 25 degrees C, 50 Fahrenheit, just going through the valve. Well, if I have a gas that's close to saturation temperature, I can suddenly create liquids in a place I wasn't expecting. And so C2+ becomes something very important to understand when I think about my gaseous fuel. And then in terms of low BTU gases, there's a lot of industrial processes where there's waste gas at the end. You could put it in the boiler, but even better if I can stick it in the gas turbine and create electricity as well. So there's a lot of gases that have, in the end, a lot of CO2 or water vapor. They're just lower BTU. So this becomes also a big challenge if you're thinking about combustion. This is a pretty big universe of problems to solve in terms of, well, what are the properties? What are the flashback tendencies? What are the mixing tendencies? If I want to meet some requirement for operability, this can present a lot of challenges. And if you design just for methane, you can be in for a surprise if you try to put a different fuel in. So that's really my session, trying to go from those trends to looking at what that means, the parameters that you would want to design around. We've been at it for about an hour, a little hour and a half, so I think it's a good time to take a break. Before we break, I do want to show you a fun video. This is sort of fun with combustion. So I had the pleasure about 2 years ago to be involved in trying to make combustion accessible to teach people about what's fun and interesting about combustion. So there's a series of 3 videos. We'll show them at different times. But for those in the back, we're ready to queue up. This is a behind-the-scenes shoot. This was an interesting opportunity where we got to shoot a movie in 360. But before showing the movie in 360, I'll give you this, which is a behind-the-scenes, and then we'll show you the other one later before lunch. So if you can go ahead. So today we're trying to fight fire with the sound of fire.
We're taking the actual sound of fire and inverting that frequency to shoot it back at an actual stuntman who is going to be on fire.
By taking modified speakers and using sound to disrupt fire. Basically, we're going to attack where flame is stabilized so that it extinguishes.
I am going to be lit on fire, and they are going to put me out with sound. To be honest with you, I'm a little nervous, but I have a great safety team, and they're going to back me up.
This isn't like any VR project I've filmed so far. I think it's probably going to work.
It's not so easy. The physics are very complicated. Fire remains a little bit unpredictable. I'm delighted. It was really cool. In fact, it was kind of intense. You know, the flames were kind of bigger than I thought they'd be.
It's interesting being put out with sound because you can actually feel each burst. It's not like standing in front of a fan. It actually is hitting you. You feel a physical force. I mean, it was absolutely amazing.
So fun with fire. We'll show you a little more detail of what that was, but again, just how to play with fire, which I've been doing for most of my career. So with that, let's take a break. Next part of this, I really want to talk about gas turbine combustion architectures, how they've evolved, what some of the trade-offs are as they relate to what we talked in the first part. So I'll talk about ground-based turbines, and I'll talk about aircraft engines. They've evolved very differently and fundamentally because of the different applications and constraints. So starting with ground-based gas turbines, this is an example of one. There's a whole family of gas turbines and big manufacturers, Siemens, MHI, GE. And if you say what are the common, and Saldo, if you say what are the common features, they all have to pick at the beginning the architecture of the combustion system. So I've listed three. Silo combustor is kind of what it sounds like. It looks like a silo on top of a gas turbine. And the idea is that I only have one combustion system. So that's awesome. It's simple. Air comes out of the compressor, and you have some ductwork to turn the flow into my silo combustor, and then I have fire just in one place. So it really simplifies the combustion system. But if you look at today's modern gas turbines, you won't find any silo combustors. And the reason is after the combustion process, you've got to take hot gas and distribute it into an annulus. And so I need metals that can take that high temperature. And generally speaking, the more metal I have, the harder it is on everything. And I have thermal growth. And so I worked very closely with one model of a gas turbine with a silo. And the kind of problem you get is you have the silo that then distributes to the circle, which forms the inlet to the gas turbine. And you'd find there's a temperature difference top to bottom. And then you'd find it didn't want to stay a circle. It actually wanted to become an oval. So you have seals and alignment problems. And so silos, generally, they were used in the early days, but with the high temperatures, less so. Can combustors are very common, and basically they're cans arranged in an annular configuration. I'll go into more detail. And there's some real nice things about can combustors. One is they become a unit of something to design, and then I can simply replicate it. And so one of the challenges of combustion systems has been if I want to develop the technology, how do I validate that it's good? And so typically, and I'll say later, but you'll start with your base unit, which might be the fuel nozzle. And then inside a combustor can might be a number of fuel nozzles. And then you'll have a number of cans. So for the example shown here, DLN 2.6, and I'll just explain terms. DLN just means dry, low NOx. And this is a low emissions technology that does not involve water injection. So that's why dry, low NOx. But you can imagine a machine, you have 12 cans. Inside each can, you have 6 fuel nozzles. And so from a development point of view, you have a unit, and then you scale that unit and just replicate it. So really, can combustors have had a nice feature from the development point of view. They're also a big advantage from the point of view of maintenance, because I can unbolt it. I can turn the machine off, unbolt each can, and in a matter of hours or days, I can swap out the combustion hardware, and the rest of the machine stays intact. So there's some good things about cans. The bad thing is, typically there's more surface area. I've got more hot metal. I've got to take my can and make a ductwork. It's not a full circle like the silo, but it's still a sector of an annulus. And so I have a transition piece. If I go to an annular combustor, that's kind of the simplest. I just have I start with, it's very symmetric to the machine. The output of the compressor is a circle. I go into the combustor, that's an annular passage, and then I go into the turbine. And the challenge with annular combustors is the inverse of cans. They're harder to develop. If I have a very large machine and it has an annular combustor, how do I know it's going to work well? One of the challenges of especially low emissions combustion systems is there's acoustic coupling between the flame front and either the air system or the fuel system or both. And you can't always predict all of that as well as you'd like to. In an annular configuration, you don't actually know how it's all going to work until I put it all together with the right acoustic coupling. So there's risk on the development side to have an annular combustor. And then when I want to go and do maintenance, depending how I design the annulus, if it's one continuous connection of metal, I had to take the machine apart to take the combustor out. So now I'm down for maybe weeks, not just hours or days. So there's some real trades to be made. It's not just about can this combustor get low emissions or not, or burn this fuel or not. It is around how do I develop it. It is about how I maintain it and assemble it. So those are some very basic choices that are made. What's interesting is they all exist in various forms, and I'd say as we go to high temperature, annular is sort of a path that you might want to go, but it is about retiring the risk, and it is thinking about maintenance. That's still a big trade that's done. So if we just look at how they've evolved, here's a picture really with an emissions focus. So we started with diffusion combustors, and that's basically mixing only a little bit of air with the fuel. So the overall fuel ratio is greater than 1, and that leads to very stable combustion. But the NOx can be high, up to 300 ppm. The nice thing about it is it's very fuel flexible. Because it's a stable flame, if the fuel properties vary, like the properties I told you about before, the flame's lit almost no matter what. So it's very good. It's also, I can have very simple fuel system. I can typically have, very simple fuel manifold, maybe one control valve, and just run the engine. So it's a very simple system, but the problem is the emissions. And you'll see, in the end, you have a lean overall system. So there end up being holes. If you look closely at that green image, you'll see some holes around the circle. So there's dilution air that's mixed in. And so that's really where the industry started. And there are some versions that have multiple nozzles like this one. There are some versions that have just one big nozzle. This is so-called multi-nozzle configuration. It was found to be more stable, and it's used when you have gaseous fuels that vary with properties. This is just a fantastic combustion system. And it can work very well for low BTU gas, because low BTU gases actually have their peak firing temperature, even when it's a rich flame, is not so high. And so the emissions aren't necessarily as high as they would be on natural gas. So that's sort of the starting point, and you can see a picture below of how those cans are then configured in an annular arrangement that would flow into a turbine. DLN1, this is dry low emissions 1. This was developed in the late 1980s and really introduced to the field in the early 90s. And this is a very interesting design because it hung on to some of the features of diffusion combustors. Imagine the same head end that you see in that green picture. And then what happened is it had a fuel nozzle that stuck further into the combustor. And then there was, I'll try to show you here with the mouse. And then there was a contraction. And literally you could have a flame upstream of the contraction. And that would be how you would light the machine. But then you would transfer all the fuel to this center fuel nozzle, put the flame down here. The flame up here would extinguish if I pulled the fuel out during that transfer. And then I'd put the fuel back in the head end, and the head end would now become a mixer. So I'd go from kind of diffusion flame to now a head end mixed fuel, but the flame would be down here. And this chart at the bottom explains a little bit of that staging, so that by the time you're above 50% load, you simply have flame downstream, even though I'm adding fuel in both places. And as you can imagine, when you have this aerodynamic barrier to the flame, it's not perfect. And so depending on the fuel quality, or depending on the temperature of operation of the machine, some degradation mechanisms, you could get flashback to the head end. The nice thing is this combustion system was designed to have flame in the head end, so other than say a short burst of high emissions, you could reset the machine and put the flame back downstream. So DLN1, very successful. It was used primarily on EClass gas turbines. The inlet air temperature wasn't so high. The flame temperature wasn't so high. Just an awesome technology. And it was initially applied to the first F-class gas turbines, and then it wasn't so awesome. Higher inlet air temperature, more fuel and air going in because hotter machine, and the flashback issues became higher. So there was a need really for a new technology, for a fully pre-mixed technology, and that's where DLN2 was developed. And there's similar technologies, but by other companies. But they're fully pre-mixed. They're characterized by a couple of key attributes. Fully pre-mixed, that means fuel is mixed with the air well before where you have combustion. Very low emissions. These were introduced between 25, but pretty quickly demonstrated 9 ppm. And they're also characterized by more complexity. So I mentioned fuel staging. It was learned that to start from ignition of the engine all the way up to full load, that you had to stage the fuel and air, and if you didn't do it axially, the way I showed you for DLN1, you had to have some fuel nozzles, and there were different versions. Some fuel nozzles had a diffusion tip and a premixer. Later version was only premixed, but then you'd turn off some nozzle, turn on others. Typically 4 fuel manifolds for a DLN2 system. And so that's more piping, that's more control valves, that's more controls for controls engineers to worry about. So more degrees of freedom, but the real advantage is getting this very low emissions. And the latest versions, I've got a chart which shows this, but E-Class, we're down to 3 ppm limit commercial operation. So they're doing like 2.5. And F-Class, the DLN2, we just in the last 2 years demonstrated 5 ppm commercial operation. So this really represents just a fantastic understanding of the technology, really minimizing variation of the airflow. So you have the air going where you want to, the fuel goes where it wants to, controlling combustion instabilities, and getting to these just remarkably low emissions level. So for ground-based gas turbines, this is kind of state-of-the-art. There are similar stories for annular combustors as well. And what's interesting, though, is just at a very fundamental level, I mentioned trades between annular and cans around development and maintenance, but there is one other difference. An annular combustor has more acoustic modes available to it. You can have axial modes, you can have circumferential modes, and you can have transverse modes. Many acoustic modes available to that cavity. A can combustor typically has only 2 modes. It has axial modes and transverse modes. And it's just been interesting as I've watched the development of combustion systems. Although you would think we would understand combustion dynamics and in the end they would all get to, say, 3 or 5 ppm, you don't see annular combustors below 9. So I don't know exactly how much that's to do with these modes, but the more modes acoustic modes that a combustion system has available to it, the more that it has a chance to be excited. And that just typically, to mitigate that, usually there's a compromise on emissions. is some unmixedness is how we solve some of the combustion problems. So, we'll see. I think there's a path to control dynamics. There's been lots of technology development. So we may see annular combustors with 3 and 5 ppm, but I haven't seen it yet. So if we say, what does a flame structure look like? This is a movie. Unfortunately, I couldn't get it to work last night, but I think you can see if this was a 5 fuel nozzles around 1. This is a quartz liner so that we can look inside and see the flame structure. And it actually doesn't matter that the movie's not working because there's not a lot to see. It's blue. So blue is good because that suggests that I don't have, so yellow is typically soot that's formed in the flame and then it's glowing. So that's why you see yellow. The only thing that's not blue in this picture is there's some seals that are getting pretty hot in the corner. But other than that, from the flame itself, it's just luminous. This is mostly CH emission, CH and C2, both blue. And this is what you want to see. If you want a low emissions combustor that's well behaved. And then if it doesn't have dynamics, it just sort of sits there. If it's unstable, you'll see a lot of motion of the blue. This was, like I said, the movie's not that different from the still image. It's just very stable flame. And the heat release is happening in typically, most of the heat release is done in about 1.5 diameters. So you see the diameter of the combustor, and it's between 1 and 1.5 diameters. Pretty much all the fuel is oxidized to combustion products. I mentioned that there are other configurations of gas turbines, and from a thermodynamic point of view, one of the interesting things, if you look at your thermodynamics textbook, it'll talk about Brayton cycle, and often on the next page it'll say a way to get even more is to, instead of having that spiky TS diagram, what if I add heat at constant temperature? And the benefit of that is once I have a technology that lets me take a peak temperature, why don't I just keep at that temperature? So a reheat turbine, this is Alstom design GT2426, and the flow in this case is from right to left. So you have your main combustor here. This is an annular combustor. Then you have one stage of turbine, so you reduce the pressure by about a factor of 2, and then you have a second combustion chamber. So you're really just, it's a double hump, and that, from an ideal point of view, is a better cycle than a single heat combustion system. And this works. It's in the field. What's interesting when you just compare pros and cons of technology, this cycle has, in the end, 2 hot sections. So you have a high-pressure turbine, which takes the full temperature, and then you have the first stage of your low-pressure turbine, takes a similar temperature. And this is where economics start to become important. The most expensive parts of the engine are the hot gas path. And the first stage nozzle, the first stage turbine, are the most expensive parts of the engine. And this engine needs 2 of them. So there can be an incremental benefit in terms of efficiency, but I have a more expensive machine, and now it's a trade. In a high fuel cost world, this is an advantageous place to be. If you're in a low fuel cost world, it's not so clear. And if you look at sort of the market penetration, it hasn't progressed as far as you might think. And I think it's because of in the end, fuel cost. There is also, you can draw an ideal cycle, and it's awesome. And then the reality of cooling lots of metal surfaces and all the losses, all the extra cooling air that's needed, you don't necessarily reach the full entitlement of a reheat cycle. So the reality of cooling metal structures, the reality of cost, make this, certainly in the running, but not something that stands out in a huge way. But the other, from a NOx point of view, this actually is a very cool design because you get the benefit of so-called NOx reburning. One of the interesting chemical reactions that happens is if I have hydrocarbon fuel fragments in the presence of NO, pretty much 1 for 1. Anytime that collision happens, the hydrocarbon is going to react with the NO. And so I'm going to actually reduce the emissions. And so this was actually marketed as a no-NOx burner, the second sequential burner, and it wasn't, it was no NOx, but there was some thermal NOx being made, but there was some NOx reburning going on, and then net was really no additional NOx. So very exciting kind of from that point of view, and then it's just, you know, what wins in the market. Switching over to aircraft engines, if you want to get low emissions, you know, I just put some of the key thoughts. It's true for any design, whether it's ground-based or not. If I inject fuel for more points, if I get more air to the head end, so the overall fuel-air ratio is leaner, then I can get emissions lower. These are just a couple of images of different systems. In the end, both those first two comments, mostly the fuel injection points, it leads to more complexity. And I mentioned for ground-based, you have fuel staging, and that's complexity. It's true on aircraft engines as well. So, you know, if you're looking at the weight of an engine, you really hate to add another fuel manifold because of the weight. But once you have it, it gives you tremendous control. The GE90 originally came, it still is a DAC configuration. DAC stands for double annular combustor. And the double part here is really, I have one set of fuel nozzles here, and then I have another set down below. Originally, those could be staged different from each other, and then there was a learning of how to really get the same emissions by keeping equal fueling. But this was really a design of getting more air to the head end, plus just distributing the fuel injection out so that I can get more mixing in a short distance, and that led to emissions improvements. If you remember back to the chart of CAPE emission standards, DAC was one of the leading ones. And Rolls-Royce has some very interesting technology. They've got more of a single annular configuration, but have also done work to get better fuel-air mixing and modify the air to meet those CAPE standards. Just to see how it's evolved a little bit more, again, the story, you started with single annular combustors, so-called SAC. There was work done from the original standards, the original SAC combustors. They had very high emissions. And then with some attention for what I just said around fuel injection, a little focus on mixing, you can still be rich burning, but it ended up being, as a technology insertion, 54% margin to CAPE 2. So that was really that's how emissions are talked about in this world. It's really, what is your margin to the standard? And so this had huge margin to the standard. It was proven, required no fuel staging, and as a low emissions combustor, did very well. And this was especially popular in Europe. Some of the airports had standards around emissions. In fact, there was a landing tax that was paid if you had high emissions. So this was a great incentive for the industry to develop technology like this. The next version was so-called double annular combustor. I showed the example from GE90. There's also a version done for CFM56. And this one actually was done first. You can see it had 47% margin, and then modified SAC got better. But this was staging, shorter combustor. That was important for GE90. It was both a combination of circumferential and radial staging. Also a lot of flight hours, very reliable, durable, and worked well. But at the end of the day, not as low emissions, not getting close to entitlement the way you would with lean burn, and really being much better mixed. And so just like DLN2 was an advantage over DLN1, going back to a single annular combustor, but with more mixing than this double annular, was so-called TAPS, twin annular premixing swirler. And this technology it's really, as we say, lean burning, because the overall fuel-air mixture is lean, but it's more partially premixed in the fundamental sense. Because it's so short, you don't get the degree of mixing that you get in industrial gas turbines. But you do get, this case, very good margin to CAPE 6, so note the difference in standard. Shorter combustor, simpler in the sense it's only a single annular, but notice how opened up it is, really opened up compared to that original SAC combustor. And there is staging that happens within the fuel nozzle. So it's a more complicated fuel nozzle. It's got a pilot and a main, and very, very successful technology from an emissions point of view. And it first came out for the GNX engine, which is on the 787, Boeing 787. It is part of what's now called a LEAP engine, which is new on the narrow body, the latest generation of narrow body, and this technology, a further refinement of it for GE9X. So lean burn for flying is really the way to go for the lowest emissions. What's interesting is that, unlike on ground, there's less commercial benefit to beating, the regulations. And so I would say this is an area where, as technologists, you can do an outstanding job. But if you end up with a technology that's a little more expensive, or in this case heavier as well, does the market really reward you? And it's a great thing to have, but I will say the market is not rewarding it the way they do on the ground as much. But it is great. It is. These technologies are really avoiding tens of millions of pounds of NOx being put into the atmosphere. So really, really outstanding from that point of view. And just to give you a sense of how this looks, I showed you an image of industrial gas turbine. These are images of exactly the same rig. So take a high-pressure test rig, take one fuel nozzle, single nozzle rig, have optical windows so you can see inside. And you'll notice that there's a yellow flame and a blue flame from almost the same view factor. And the yellow is when you have the pilot only. And so you need that to start the engine. You need that at low power. And so pilot becomes very important, especially for an aircraft engine. You want the flame to be lit. You don't want to have a flame out, just critical to flight operations. So you design a combustor with a very, very stable mode of operation. But then you add a mixing, this main fuel air passage for mixing. Now it becomes much bluer, not quite as blue as that industrial flame I showed you. So again, it's more sort of partially premixed. It's also liquid fuel, which is harder to mix. And then if you look closely at this image, this is an optical rig where a laser sheet was added so we could do some interesting imaging of fuel particles as well as look at the flame structure. But it's just amazing to see what happens inside an engine and understand that you can have very different flame structures and different aerodynamic structures for flame stabilization. And if you do that right, you can have this great balance of great operability as well as very low emissions. And that becomes part of the art of combustor design. It's really that thoughtfulness around the basic aerodynamics and then how I add fuel and where the flame ends up being. So this is part of the fun of really designing practical combustion systems. So if we talk about, so I've given you sort of an overview of architectures of both for ground-based and flying engines. Now we'll go into a little more detail of the development. And I'll just, pause here and just think about all the things that a combustion system has to do. And I've alluded to many of them. But before I show you sort of all the details, I just want you to imagine in your mind, if you had to design a combustor, what are you designing it for? We've talked a lot about emissions. Great. But think about how an engine operates. I've got to start it. I've got to accelerate from not working. I've got to ignite it, start it, accelerate it. I might want to run it at low load. Think of an aircraft. It's taxiing down the runway, very low power. And then a minute later, you want full power because I want to be able to take off and go down the runway at high speed. Then I'm up in the air, and I don't, it's very different inlet conditions. I can go from, say I'm in this part of the world, I'm 40 or 50 degrees C in the summer on the ground, and then all of a sudden I'm at minus 50 when I'm up in the atmosphere. So I need a combustor that can operate over those huge range of conditions. And then I've got to be cost effective, and I've got to be able to maintain it. So when we think about combustion design, these are just some of the factors that you have to think about. I just want to pause and just, having been involved in development of combustion systems, there's always great ideas. People always have just amazing ideas to design new features. And what's interesting and very humbling when you're in this line of work, if you have a combustion technology and an idea that does, let's say there's, I didn't count them all, but, and this is maybe an incomplete list. So imagine you have 20 things that a combustion system needs to accomplish. What happens if you get 19 out of 20? Do you have a combustion system? You don't. I was with one where it did everything but start. That's hard. Because once it was lit, it was awesome. Okay, but lighting it off and getting the right combustion efficiency at very low power, it didn't do that. So you think about it. If you're in a class, you're in an exam, 19 out of 20, that's 95%. Most places that would be an A. In this world, 19 out of 20 and you failed. So that's the humbling part of design. And that's why there's no best design, and we're going to do an example this afternoon. You really want to think about it's a balanced design. And it doesn't have to be perfect in every one. There's some minimum requirements, and this is where you get into what's my spec limit, what's my target, what's the either lower or higher spec limit I want to achieve. But that really is why this is an exciting field to be in and exciting work to do. It's achieving that balanced design. We have analysis tools. We have validation. If you think about work you are doing as part of your research, it's enabling this. And you can spend years on any one of the words on this page. Whether it's P4 prime is what we term combustion dynamics. That's pressures that fluctuate compared to the mean. Reliability. So here's an interesting question. How many people believe aircraft engines stay on, and let's just pick a very common engine. Boeing's 737 has CFM56 engines. How many of those engines could stay on wing more than 5 years? Think they can be on the wing for more than 5 years? So you're right. But that's incredible. Imagine bolting an engine to a wing and saying it's going to fly every day and it's not going to come off wing. Now, that doesn't happen to every engine and doesn't even happen for every airline. But there are airlines who are very disciplined. They follow the manual. They're careful on how they fly the engines. And they get 5 years of operation. And there's only limited sort of on-wing maintenance that you can do. So it's just amazing to have these machines, which are marvels all by themselves, and then they have reliability. So we have folks who can spend their entire careers focused on reliability and durability. If you think about the more aerodynamic part of combustion systems, the fuel air mixing, that gets into questions of auto-ignition and coking. Coking is fuel deposits. There's two places that's important. One is in the fuel system before the fuel meets the air, and then there's once fuel meets air. And there's different mechanisms behind coking, very, very complicated. Smoke and particulates and emissions, right? Very complicated. Those who are involved in trying to predict particulates, hundreds of species, thousands of reactions. We don't really understand all the details. And yet we need to have engines that don't make smoke. And it's very interesting. If you look at old movies where they have airplanes, you'll often see a smoke trail behind them. If you look at airplanes today, very seldom you'll see a smoke trail behind it. So really a tremendous amount of work. But I just want to pause on this page. There are just so many things that you have to keep track of, and it's exciting. So, part of this, and this is what, again, makes this field so exciting, there's complicated physics, and there's nonlinear interactions. If you think about combustion instabilities, there's just a huge range of time and length scales, and there's trade-offs that are required to meet the product requirements and to get balance. So again, for me, there's never a best combustor design. It's simply, is it balanced and does it meet this range of criteria? And as we go to higher pressures, higher temperatures, have these demanding emissions requirements, it's just hard. And I think a lot of what was said yesterday for reciprocating engines, many of the same trades are involved. That's what makes this exciting. So when people ask me, just how do you articulate some of those challenges? So here's just a couple. If you're talking to your your friends who maybe aren't in this field, and they say, well, so what's hard about what you do? So imagine anchoring a flame in the equivalent of 100-mile-an-hour wind. That's what happens inside these engines. Imagine chemical reactions that occur, a fraction of a second as the fuel and the air flow through. And fraction of a second, what do I mean by that? Those large industrial gas turbines I showed have a combustion residence time of about 30 milliseconds. So think about that. 3/100ths of a second is the time it takes for the air to get from out of the compressor into the turbine. It's only there for 3/100ths of a second, 30 milliseconds. The latest aircraft engines are somewhere between 2 and 4 milliseconds. So that's not much time. And think about all the chemical and physical mixing processes that have to happen. So, how fast? Roughly 3 to 25 milliseconds. So that's really cool. That's just part of the fun. So what are the key physics? If you're going to design a combustion system, what are the things you have to think about? So I'll just walk from front to back. This is a cross-section. This is an image of a large eddy simulation of what's happening inside a can combustor for an industrial gas turbine. And first of all, you have kind of a lot of length at the front there where it's all black. That's sort of the head end where you're getting the air conditioned to flow with the right velocity profiles, with the right turbulence intensity, and then it meets the fuel. So fuel air mixing happens there. And typically it's turbulent and subsonic flow. Then you can have chemistry starting in that mixer. You don't want to have too much. So most of the chemistry happens in the flame stabilization region. Many combustion systems practical are some combination of swirl-based stabilization and bluff body. So there's an expansion that happens with usually some sort of edge, a dome or a cap. Different words are used in different industries, but there's an expansion. But often there's a lot of swirl added to the air as well. That creates a stable flow structure to capture the flame and enable recirculation. So typically a combination of swirl and bluff body. The other reason, if you think about it, when I release heat, I get an expansion. And the typical expansion ratio is about a factor of 3. So the density of air is whatever it is. I add heat, and it goes up by about a factor. The density goes down by a factor of 3. So if I kept the channel the same cross-section, the flow would accelerate by a factor of 3. So what you'll see in most combustion systems is that there's something like a factor of 3 expansion. And then the velocities through the system don't change that much. So that's, if you look at, and it's hard to see in a cross-section of something round, but that's roughly the expansion ratio in a system like this. So you have all the physics of ignition. You have extinction. You might have some stability questions. I said there's acoustic modes of the cavity. There's a flame, and they can connect and start to interact. In terms of getting emissions and getting complete combustion, turbulence chemistry interactions. And we heard some very good fundamentals on looking at the structures and what's really going on in these turbulent flames. There's heat transfer to the walls. There's convective heat transfer, but there's also radiation heat transfer. And for liquid fuel systems, that radiation can be a big deal. And then typically for a gas turbine, you need to accelerate the flow. I'll talk later this afternoon about, why you don't want to release heat at high velocity. So fundamentally, you want to release at relatively low velocity all the heat, but then you got to accelerate that flow through a transition piece and a turning nozzle. And so you're accelerating pretty much to sonic conditions of the gas, so it's choked or near choked. It's transonic in that region. So you think about the very hot gas, very high pressure, and now you're going very high velocity, so the heat transfer coefficients are very high. So those are, if you're thinking about designing a system, these are some of the key physics you got to keep in mind. And on the previous page, we had seen, we had seen some of the requirements that flow down from the engine. So with those physics in mind, I just wanted to walk through, some of the fundamentals and just really go through a little bit more detail on NOx. So there's really three. I mean, there's different numbers you could have. I have three on this page of NOx formation mechanisms. Zeldovich is one, and that's really the chemistry of high temperature air. So Zeldovich was the first to really identify and communicate that N2 plus O or O plus N2, the atoms interacting with diatomics both ways that lead to NO are fundamental. And what that means, if you look at the scaling, because of activation energy, the rate of formation of thermal or Zeldovich NOx is exponential with temperature, and it's linear with time. And I talked about combustion residence time earlier. One of the reasons to go from 30 milliseconds to 5 is the less time I'm hot, the less NOx that I make. It's as simple as that. But the other part of that is shown in this chart. If you look at flame temperature on one axis, and here we've got a nice combination of Kelvin and Fahrenheit, depending how you think. The other side is sort of the rate of production of thermal NOx. And what you'll see is, and that's this dotted line here, that the formation rate is very high, right around equivalence ratio of 1, and it's not so high further away. So the way to avoid emissions and thermal NOx is either to be rich and so rich that it's not that hot, or lean and so lean it's not that hot. And so that's really, this on one page really describes the fundamental reason we go to lean premix system. And so I can be lean and premixed, and depending on the flame temperature, ideally I never get hotter than I need to be. Now in practical systems, you have cooling air. You may have parts that go together with seals and there's leakage. So typically we'll talk about a reaction zone, which is a higher temperature than the turbine inlet temperature. And then the challenge becomes how to make the reaction zone temperature not that much higher than the turbine inlet temperature. But by staying on this side of the curve is how you can get to emissions like we've talked about, 9 ppm, 5 ppm, and so on. There is technology, and there are designs out there that start with burning rich, and then they kind of have a tunneling idea. So if I can mix faster than chemistry happens, I can tunnel underneath this peak. And so rich, quench, lean, RQL combustors is a basic strategy that has been adopted as well. And so the art there is, can I get mixing to be fast enough? And in general, just staying lean and being lean is good, but there are times when RQL makes sense. One of those times, and I'll jump to the third mechanism here, fuel-bound nitrogen. Depending on your source of fuel, some fuels contain nitrogen, and that's can happen in liquid fuels. If I burn lean, then then really all of the nitrogen that was in the fuel becomes NOx. So what happens when I have a fuel? If I have a fuel that has 1,000 ppm of nitrogen in the fuel, it won't be 1,000 ppm in the exhaust, because fuel in the end is about 5% of the mass flow of the machine, but it'll still be tens or maybe hundreds of ppm. If I were to burn rich, fuel by nitrogen forms, one of its intermediaries is HCN, and there's a nitrogen recycle loop that happens, and I can take HCN and go to N2 instead of NO if I'm on that rich side. So, if you had the problem to solve of take a fuel with lots of nitrogen in it, that would be a great reason to think about an RQL combustor. The other mechanism, it turns out that it's not nearly as big a factor as Zeldovich, but prompt NOx. And I just wanted to pause on that. Sumitra mentioned this morning, but I wanted to just give a little more insight. That's also known as the Fenimore mechanism. It's not nearly as well known as the Zeldovich mechanism, but it does give credit to key people in the field. And I just wanted to spend a moment and give a tribute to that discovery. Professor Dibble talked about that what's interesting about these classes is we teach you stuff as if we knew it all along, but really how science happens is people have discoveries, and we reorient our thinking, and then we teach it like we knew what it was. But back in the 70s, Charlie Fenimore was doing some very basic studies to understand NOx. And so he set up a porous plug burner to create a 1D and well-characterized premixed flame. And he put a NOx probe into it, and he expected the Zeldovich kind of mechanism. But he tested that idea. He said, well, if I take the mechanism of Zeldovich, I shouldn't see much NOx at the beginning, and the further we go downstream, the more and more NOx we should see. And so he made the observation that there was NOx, near the frame front. And in fact, it was higher than you would predict based on what was known of the Zeldovich mechanism at the time. So he had the curiosity to say, well, what else could be going on? And he did a lot of work in elementary chemical kinetics. And so he postulated that it was hydrocarbon fragments. I've written one of them here, CH plus N2, but there's also potentially carbon atoms plus N2 or CH2 plus N2. So there's a family of reactions that in the end all go after nitrogen. Nitrogen is a very stable diatomic molecule, but with the right reactivity, you can break it apart. In this case, form a precursor to NOx in a high oxidation environment. So Charlie did that, and I just wanted to give credit that this is a Combustion Institute, Combustion Summer School, and back in 1974, he was awarded the Bernard Lewis Gold Medal, as noted here. So, if you think about careers, there's awesome careers to have in academics, and there are awesome careers to have in industry. And I think Charlie Fenimore is one of those guys who always maintained a focus on fundamentals and applying those fundamentals to practical problems. But he did it in a way that really had lasting impact, and the prompt NOx mechanism is his. That was his discovery. So when you think about NOx control, one of the questions is, so why do we do lean premixed? And so I pulled this up. This was an EPA report, and it looked at the cost impact of different control technologies. So, one thought is, well, we'll just put aftertreatment on. The combustion system does its thing, and it's hard to mess with combustion, so let's just put aftertreatment on. And so you can put so-called SCR, selective catalytic reduction. There's low temperature versions, there's high temperature versions, depends on the temperature of your exhaust gas that you're starting with. But fundamentally, if you look at the cost, and this was cents per kilowatt hour of power production. This is a fairly dated, I think it might be 1999 publication. What's interesting is the conclusion was that dry low NOx had the lowest number, and it was almost independent of the scale of the unit. So if you ask the question, why have we invested in dry low emissions technology as an industry, it's really because that's the one that makes sense. If you can, and I've always had the belief, if you can fix the problem at the source, why deal with it later? And so if you're going to fix the problem at the source, how do you do that? As I showed on the previous page, it's really about lowering the peak temperature. So premixing the fuel and air. It can also be reducing the O2 concentration. Adding water, so dry low NOx was really, that term comes from when NOx abatement was, well, let's just put some steam or liquid water into the combustion system. You can do that, and you can actually get remarkable reduction in emissions when you put about an equal mass ratio of fuel and water. But that's a lot of water, and because it's high temperature environment, you have to be clean water, otherwise it makes scale inside the engine just like what happens in a kettle. So you need to have expensive deionized water, and it's just a continual cost. It's like a fuel cost. Maybe not the cost of fuel, but not that different. after all the cleanup and everything. So you can lower peak temperature by adding a diluent like water or steam, but fundamentally just premixing the air is good. I mentioned that NOx reduction is linear with residence time, so reducing that residence time, making sure I have fuels that don't have fuel by nitrogen. And then there's other ideas. You can stage combustion. I showed one version of staging. Another version of staging is like the reheat combustor, adding more fuel later. And that's one of the latest technologies that's all inside the combustor. And then, of course, I can do after treatment. So I put in bold, where we've really put our focus, reducing the peak temperature and reducing the residence time. And because of cost, that's really the preferred solution. So what are the implications of that? Well, as I mentioned for aviation, same thing here, more fuel injection points, more air to the combustion dome at the cost of fuel system complexity. But there are constraints, and we could talk about the constraints for dry low NOx in terms of the box. First of all, you hope that there is a box with a space inside it. Sometimes you wonder if you're a combustion engineer, because you have these different things. And I'll go into it on the next chart, but NOx is what you're after. You want to minimize NOx, you want to minimize CO, but turn down. I got to be able to turn down the machine. I have to be able to run wherever my customer chooses to run the equipment. And then I worry about combustion instability or dynamics. That's pressure fluctuations. And dynamics are dramatic, I'll say show of force of physics. You can have a very happy combustion system. It's just running the flame stable. It's all good. And then it can trigger in a very unsteady way into a mode where I have peak-to-peak pressure fluctuations of 5 psi, 10 psi. I've seen 20. And those are remarkably destructive pressure waves. So dynamics is the thing to really get a handle on. A lot of work has been done by the technical community to understand the basic physics, to be able to predict it, to be able to mitigate it. But that's been one of the challenges, and I'll go through that in a little more detail on this page. So if you think about an operating window of a combustor, one axis to draw is just the fuel-air ratio, because it does vary over the course of an engine. Typically at high load is when I have the most fuel given the air. But a gas turbine is basically, you can think of it as a constant volume device. It pushes air through the system. And there's inlet guide vanes that vary the pressure. But once I'm at full speed of a machine, I'm basically like a fan. I'm just pushing volume through the engine. So if I want to make low power, I have basically the same amount of air, but I have to put in less fuel. So that means I'm on the lower side of the equivalence ratio. So I have to be able to operate over a range. And as we go through this, Knox and Zeldovich mechanism would tell me, well, I want to be, and I've put here a black line suggesting for each parameter I'm going to show you what the acceptable limit. So for this combustor, you'd say, well, based on Knox, I could go almost to phi of 0.65, say phi of 0.662. So above that, I'm going to have a problem with NOx, but as long as I keep the fuel-air ratio, and that's good, I can design and ask the question, how much air do I have to put in where I'm putting the fuel in so that I stay in this range? So that's good. If that was the only problem to solve, maybe we could go to lunch early. But I do need to be able to turn down, and what I find with CO is that CO typically is low, and actually this is not intended to be zero because you get equilibrium CO at high temperatures, but that's typically in the couple of ppm range. But I can go pretty quickly as I go leaner to 10, 100, and because of nonlinear behavior of extinction, I can easily get to 1,000 ppm of CO even more. I think I have a happy flame, and it is stable. It's good from that point of view, but I can have a stable flame that has 2,000 ppm of CO. So again, if I have a limit, typically CO limits are similar to NOx. If it's 25 for NOx, it'll be 25 for CO. So that now defines a window to say, well, now I've got to manage my fuel-air ratio within, say, 0.42 and 0.62, let's say. Not bad. I can work with that. But this starts to tell you why we do staging, why I have more than one fuel manifold. And just a thought on that, people talk about air staging. and you can do it. But if you think about air staging versus fuel staging, fuel is only 5% of the mass of what's going through the machine. So if I have to design valves and pipes and stuff, I have a certain size of equipment. If I want to stage the air and I want to, say, move air and take it off board and stick it back in somewhere else, I'm now having to move 95% of the mass. And by the way, that air is hot because it's been through a compressor. So when you think about the choice between would I stage fuel, would I stage air, fuel's cold and it's only 5% of the mass of the machine. As much as it's a pain to do fuel staging, it's more painful to do air staging. Although there are machines out there and people have designed and built satisfactory systems with air staging, but I would argue they're probably higher cost and maybe less reliable than fuel staging. So within this frame, you think if it's just about emissions, not too bad. But then you sort of learn things as you run this. So you build it, you design it, you run it. And then you have these tones, and these can be combustion acoustic tones. And you can find that as you go colder, lower fuel ratio, all of a sudden, I get a mode that shows up. Might be, 200 hertz, something like that, depending on the size of the machine. And then you go, so I can't really go too low. And then you say, okay, I'll just add more fuel. That's good. Make that cold tone go away. But pretty quickly you run into another tone, so we'll call that a hot tone. And all of a sudden, you find yourself in this interesting spot where how big is my window? That's why I showed that box on the previous page. How big is my window where I can work happily? And all of a sudden, you might find that, wow, to meet both emissions and dynamics, I've got this pretty narrow window. Now, would this ship as a product? It would not. Okay, so this would be a case of I didn't get 100. I didn't pass. If you were having a design review, you'd be told to go back and fix this. But this is a great way to think about when you're designing a combustion system, what are the limits that you have to deal with? And so now you have to say, well, what problem do I want to solve? In this case, NOx and CO aren't the problem to solve. In this case, it's about how do I broaden my operability limit? And then it gets into what are the physics of that and what are my design choices that I can make. So this is what combustion designers do. And it's a challenge, but it's also very rewarding when you're done. And so I just wanted to show you this page. I think I've said most of this up to now. But starting with the baseline, this is the same chart I showed for efficiency and firing temperature, but I've added here, starting with the baseline of hundreds of ppm. We started EClass back in the late 80s, early 90s at 25, and the most recent version and uprate of that machine is now 3 ppm. F-class started at 25, pretty quickly got to 9, and then just in the last couple of years has demonstrated 5. And then we're still kind of hanging on for the HA, and HA stands for air. Remember I said there was a steam-cooled version, but the current ones that we're on now, the very high efficiency I told you about, those are air-cooled machines. And we're hanging in there at 25. So I don't know that we're going to get to 5. You start to look at what entitlement looks like. And at the very high firing temperatures, it's a challenge. I do think there's a path to get, even at those cycle conditions, well below 25. That's the challenge for your generation and beyond to think about how to do. So those are just, great example of how it's all come together. The question is, so how do you do that? I talked about some of the things we need to do. I just wanted to show you just sort of what the design and validation process, what are the elements? Typically, it starts with some sort of simulations, and it evolves to experiments. And so 0D, 1D, a lot of stuff you can do. Chemkin, you heard a lot about that in the last couple of days, whether it's perfect stirred reactor, plug flow reactor. You can take a lot of the elements of what I showed you and simplify and say, well, let me just think about a residence time in this zone. And so whether it's a zoned model or a simple plug flow, so it could be a perfectly stirred reactor, for example, to be the flame stabilization region, followed by a plug flow reactor. In its simplest embodiment, that's a great way to analyze a combustion system. So you do that. Then you might do some non-reacting simulations. You look at the basic flow structures. I mentioned you can be bluff body stabilized, you can be swirl stabilized. That image here is actually showing cooling, because I got to keep the walls cold. So maybe you have holes in the walls and you do non-reacting simulations. And then you go to a full-bore reacting simulation. And if it's gas fuel, that's one level. Gaseous fuel, it's one level of complexity. If it's liquid fueled, it's another level of complexity. I will say there's been tremendous advances in the last 10 years, really 5 years, about industry adopting large eddy simulation. The unsteady characteristics of LES really make the simulations much truer to the physics that you observe when you actually build and run these things. So tremendous progress, but as you go up, the time, cost, and fidelity also goes up. The cost of running a supercomputing simulation is, and that's why it's not intended to be totally the scale here, but the notion of going up is you like the fact that fidelity is getting better, but you don't like the fact that the time it takes to do it and the cost is getting higher. So full reacting unsteady simulations are becoming expensive. The flip side is I can build it in hardware. So I can build some subcomponent rigs, non-reacting. If it's liquid fuel, I want to study the basic interaction of fuel-air mixing. Where is the spray? How is it going? If it's atomization, key question is what is the drop size? Once I know drop size, I can start to calculate droplet lifetime and evaporation timescales. So you do work at subcomponents, then you put it together as a single nozzle. I showed you some images of what the kind of flame structure you get if you have windows in such a rig. And those are extremely valuable insights. You know, combustion does scale pretty well. So if I can learn at the single nozzle level, that's fantastic. We also have rigs that are more like sector rigs. That's the image shown above. Because if I want to look at flame propagation, I want to light it here, and does the flame propagate to its neighbor? I need to have more than one. But you can get a lot of knowledge out of single component, and single nozzle and sector type rigs. And those are relatively low cost to run. Then you get to full systems. So whether it's a full can, like I talked about, or say a full annular rig if it's an aircraft engine. Aircraft engines typically are small enough that we can do a full annular rig in a way that we could do a can combustor for a large industrial machine. But those become expensive. You know, the cost for a day of testing, well, there's several costs. There's the cost of the rig itself and the facility. There's the cost of the hardware that I put into it. And then there's the cost and just the sheer energy. I have air compressors. I've got fuel systems. I got water systems. So the whole infrastructure required to develop and validate combustion systems is big scale. And then, of course, I get to the full engine. And so that's been an evolution over time to avoid surprises for customers. Even ground-based gas turbines are now typically tested in the factory. And those facilities can cost hundreds of millions of dollars. And then full-up engine tests for aircraft engine, both engine tests on the ground. There's also flying test beds, taking things like old jumbo jets and strapping whatever engine you have and learning how it works up in the atmosphere before it's actually flying the engine or flying the aircraft that you've designed it for. So these are some of the key elements of the design process. And I wanted to share with you kind of an interesting thought of where we're going, because we have been in the world that experiments are so expensive, I should do simulations first. But as you know, for those involved in CFD, it's not so easy to go from geometry to mesh, put boundary conditions, run it, and then analyze the results. So we're entering a whole new world. And I want to give a plug for a new technology called additive technology, 3D printing. We've heard about it certainly in the context of making plastic parts and even 3D home printers and stuff like that. But here I'm talking about a couple of key technologies. This is direct metal laser melting, DMLM. But it starts with a metal powder. And it starts with making a thin layer of metal powder starting on a plate, and then literally building up in layers with typically a laser to form a metal part. So I do it's almost like microscopic welding, you could think about it. It doesn't have to be a laser. There are systems that involve E-beam. So there's other technologies that are evolving, and modalities, I'll say, of additive. But what's interesting is that enables a very fast cycle time from idea to hardware. I can now have an idea for something and 2 weeks later have a part of good quality in my hand to do a prototype. And so that's really where it started. We've been using additive technology in combustion for quite a long time for prototyping. What's new is actually thinking about this technology for production. So I talked about the TAPS combustion technology, and what you're seeing there is an image of the fuel nozzle used on the LEAP engine, which was just certified a couple years ago. And the tip of that nozzle, so the highest part up there, you see a couple holes where the fuel injection holes are. That whole tip is printed additively. Any LEAP engine that you see, that'll be on, an Airbus A320, on a Boeing 737 MAX, those have printed parts. So this is not the first certified engine part, but it's the first, I'll say, critical engine part, because you can make brackets and other things as well, but this is really a very critical part, intricate fuel passages, intricate air passages, and we're now printing by the process shown in that image, where a metal powder building it up. And so what's interesting about this, and this is something that, if you're going to be in this world, in this technology world of developing advanced machines, even in your own labs, if you use this technology, what it really means is you get complexity for free. Because really the cost of this stuff is the build times. You get so many cubic centimeters of build per hour. But what it's actually printing, whether it's a solid lump or whether it's a very porous structure, is almost irrelevant. So this is just a very exciting time, and I've challenged my own computational folks I work with to say, if you want to be relevant and you have an idea, are you faster doing a simulation first or building it and putting it in a rig? And it's a very interesting time, because now I can get to hardware in, like I said, a matter of weeks, week or two, and simulations, sometimes it's hard to get that to a week or two. But for those in the computational side, this is your challenge. How do you get to help us? In the end, it's not one over the other. We absolutely have to have both. I only learn certain things in experiments. I can't measure everything. And when I do modeling, I only have certain physics in my model. So that's where I wanted to end this section. Just to recap on what our combustion system technology drivers are. This is what I've covered this morning, and this afternoon we're going to have a lot of fun. In fact, there's two things I want to do before we break for lunch, so bear with me. One is I want to give you the challenge to think about over lunch, once I get control of my cursor here. So here is your challenge to think about over lunch. We're all going to be combustion designers this afternoon. And so imagine we're consultants, and we've had folks come up to us and say they want a conceptual design for a combustor because they want to make a small gas turbine to be packaged as part of a hybrid electric mobile platform. And that mobile platform could be for a hybrid truck. It could be for a small vertical takeoff and landing aircraft. So with all due respect to the recip engine friends in the room, this is and I'll tell you more why this is an interesting thought. Gas turbines are typically used for big stuff and reciprocating engines for small stuff. But imagine you wanted a small and efficient engine, and the question we're going to answer is not would I build it, that's a different question, but if I built, what would it look like? And then I can do an analysis of would it make any sense. So that's going to be our challenge this afternoon. The other thing I want to ask you is, I think each of you have a tag of a group number, and we're going to use this afternoon a chance to just ask you to work as teams. To each group will answer a question. So when you come back in, please sit with people that have your number. I believe numbers 1 through 10. And so please come back. We'll remind you when you come in. But you want to be near the folks with your number, because you're going to have a question to answer and share that answer with the rest of us this afternoon. So one more thing before lunch. We're going to roll, you saw that preview video of making of a movie. There's a very interesting, as I said, this was shot in 360, so actually we can't do full justice to it. But imagine that you could actually rotate around. We may do some of that here. But this is, again, having fun with fire, and this was the actual video that we made. So let's roll that and then have lunch. Fighting fire with fire. Conventional wisdom says that's an exercise in futility. But at GE, we don't pay much attention to conventional wisdom. So we're going to conduct an experiment on Jason here to prove that you can fight fire with fire. Or, more accurately, with the sound of fire. And you can actually rotate around and see that if you were to see this again. Flames, extinguishing them. Sound crazy? Well, actually, GE uses sound in a lot of innovations, including a new, more precise kind of mammogram that uses ultrasound instead of X-rays. But first, we need fire sounds. So rotate around if you can to the other direction. Oh. We'll need to mix these fire sounds to create the perfect frequency and intensity. We'll aim this sound at the fire with these modified speakers. Lots of them. Ready, Jason? Light him up. So, it seems you can fight fire with fire.
Sound.
And if we can fight fire with fire, imagine the other impossible things we can do. So it took 10 tries to get that right, by the way, so Jason got lit up a few times, but and that was fun.